So last week on Friday in particular, we focused on working through a few illustrations of how to calculate selection probabilities based off of the probabilities of observing certain samples in the population. In each of those situations that we looked at, so the earlier examples in the same lecture set, the probabilities of observing each sample were unequal. So the selection probabilities changed depending on the illustration we looked at due to the inconsistent probabilities associated with each sample. We also looked at how to define the properties of our estimators for each of the probability samples. In particular, we talked about two estimators, the estimator of the population mean, which we designate mu, and the estimator of the population standard deviation, which we designate sigma. We discussed that the ideal characteristics of an estimate would be no bias and the smallest possible variance, which leads us to what we would call a precise, accurate, and unbiased estimate. We also discussed that accuracy, let me just make sure I have this right. I always confuse the two. No, sorry. We also discussed that the accuracy of the estimate can be calculated through what is called the mean squared error. And we actually showed that when we have an unbiased estimator, the mean squared error converges or is equal to the variance. So again, the first characteristic of an estimator would be that it's unbiased. And then the second characteristic would be it has the smallest possible variance, because given it's unbiased, it'll be accurate. And then we just want our precision to be as small as possible. All right. Now what we're going to do is start to talk about specific probability sampling schemes. So this would be the focus of the course for, I would say, at least the next month, looking at or surveying different survey sampling schemes. Tried to make the survey joke work. It was a little rough. The first scheme that we're going to talk about is simple random sampling. And as I've mentioned before, simple random sampling actually forms the basis of the majority of the techniques that we are going to look at in this course. As we begin to study new techniques, what you will notice is the foundation for all of those comes back to the idea of simple random sampling. All right, what is simple random sampling? You have probably heard about this before. I know at the first and the second year level, if you've ever talked about the assumptions of the inferential procedures, you would have probably seen that the first assumption is the data was randomly selected. And most often we talk about this as being collected via a simple random sample. Okay, so there are two types of simple random samples. There are the simple random sample where each item is collected once and only once. We call that the simple random sample without replacement and designate that SRS. And then there is the simple random sample where each observation can be returned to the frame such that it can be sampled as many times, or it can be sampled little n number of times. So if your sample size is little n, you could technically observe a sample with the exact same observation over and over and over again. And we designate that scheme simple random sampling with replacement, and we call that SRSWR. So simple random sampling gives each sample in the frame the same probability of being selected. We can show that if we have a frame that consists of n possible units, and we would like to select a sample of size little n, so sorry, the frame is capital N units, and we want to select a sample of size little n, then there are capital N choose little n different possible samples of the same size that are available to us. Okay. Now, the probability of observing each sample would then be 1 over capital N choose little n in the situation where we are sampling without replacement. All right, it follows that the inclusion probability for each observation in our SRS can be calculated or derived as follows. Okay, so first, if one observation is selected from the frame, then we have little n minus 1 observations remaining. So if one observation is selected from the sampling frame, then we have, or there are, little n minus 1 observations remaining to be selected. Let's just write from the remaining capital minus 1 observations. Okay, so we have here, if one observation is pulled out from the frame, then there are little n minus 1 observations that are left to be selected from the capital N minus 1 observations that remain in the frame. Okay, so again, if the frame size is capital N and you pull one observation out for your sample, we're sampling without replacement. So that means that we only have capital N minus 1 observations left over, and we only have to select little n minus 1 observations to complete our sample. Right. So then we can say it follows that there are capital N minus 1 choose little n minus 1 observation or possible samples of size little n minus 1. All right. Okay. So then we can say the probability that observation I is in sample S is equal to capital N minus 1 choose little n minus 1 divided by capital N choose little n, which is equal to n minus 1 factorial divided by little n minus 1 factorial over capital N minus 1 minus little n minus 1 factorial and that is divided by capital N over little n factorial n minus little n factorial. Okay. And that gives us n minus 1 factorial little n factorial over n minus little n factorial divided by n factorial n minus 1 factorial over n minus n factorial, which reduces to little n over capital N. So for a simple random sample without replacement, every single possible sample from a frame, well, every single possible sample of size little n from a frame with capital N units has a probability of 1 over capital N choose little n of being selected. Okay, so 1 over n choose little capital N choose little n is the probability of observing each sample in an when using SRS. The derivation below is an illustration of how we can derive the inclusion probability for the individual unit in the sample. So it turns out that through this particular derivation, we can show that the probability of observing observation I in the sample, so that is observing one of like any of the observations from the frame in the sample, is simply little n divided by capital N. Okay. So this is our inclusion probability for each observation when we use SRS. Does anyone have any questions? All right, so for a simple random sample without replacement, we can use two estimators, or for mean, or for the population mean and for the population standard deviation, we can use effectively our traditional estimators. So for the mean, we have basically just the average of the sample that we have observed. And then for the standard deviation, we have the traditional estimator, which is the sum of the squared deviations about the population mean. Sorry, I just saw that part being. So little n factorial is going to be little n. Okay, so basically they cross out because n factorial, yeah, this will work. It's n times n minus 1 times n minus 2 times n minus 3 dot 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 dot. Okay. And then little n factorial equals n minus 1 times n minus 2 times n minus 3 dot 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 dot. Right, so capital N minus 1 factorial is everything after n times n minus 1 times n minus 2 times n minus 3. So the capital N minus 1 factorial in the numerator cancels out every single term that follows after capital N in capital N factorial. So that's how you get capital N on the bottom. And then it's the same idea for the little n minus 1 factorial, canceling out everything that follows little n in that factorial expression. Right, so basically for SRS, we just have our traditional estimators. Now we can express these estimators in terms of an indicator variable. The indicator variable here is called capital I subscript little I. And capital I is a binary variable. So it's either equal to 0 or it's equal to 1. It's equal to 0 when the observation of interest, so observation little I, is not in the sample, and it's equal to 1 when observation little I is in the sample. So for every single unit in the sampling frame, when we select little n observations, we can assign a 0 or a 1 to each observation from the frame, and every observation that has a 1 assigned to it is going to be in the sample. Okay, so the indicator, again, is simply just a representation of the values in the sample, or it's an indicator that tells us if that observation was chosen for the sample. So using the indicator variable, we can then write our estimators as mu tilde is equal to 1 over little n multiplied by the sum across every observation in the frame of little I, of capital I subscript little I times yi. Right? So these two expressions here are equal. Right? You'll notice that the only difference, and it's very subtle, is simply the subscript underneath the summation sign. In the first case, we have the sum across every observation in the sample, and in the second case, we have the sum across every observation in the frame. It follows that the second two expressions, although in this case we can't say that they are equal because in the first case I wrote it as sigma tilde, and in the second case I wrote it as sigma tilde squared. However, it's the same principle. So you can see here we have the summation over the sample size versus the summation over the frame. And in the second case, we've introduced the indicator simply to represent the fact that we are only the values that are actually chosen from the frame are going to impact the derivations of interest, or will be utilized in our calculation. So these are equivalent expressions. They represent the same thing, but using the indicator variable, we can now sum across the frame because everything that has a 0 attached to it is obviously not going to contribute to the sum. Now you might also be wondering, okay, well, why are we doing this in the first place? Like, why don't we just use the original formula where we take the sum across only the observations in the sample? The main reason that we're considering the latter cases here where we have the indicator variable is because the next thing that we want to do are study the properties of the estimator. So we want to determine if we have an unbiased estimator for the population mean, and we want to determine if we have, or we want to find the variation of our estimator so that we can calculate how precise, we want to determine the variation of our estimator so that later when we go to bound them in the confidence interval, we know how to calculate the estimate of our variation, and also because it'll allow us to calculate the precision of each estimate if it is in fact unbiased. And then if we have multiple samples, we can compare the precision across those samples. All right, so our indicator notation as it's written below is effectively more useful when we go to study the properties. That's one of the big reasons why we introduce this indicator variable. So we are going to focus on calculating the expected value of mu, mainly just to show it it's unbiased. And we are going to calculate the variance of mu so that we can later bound our estimates using, well, effectively like a finite size central limit theorem, but I'll come back to that point a little bit later. On slide 20, I have the final results. So you'll notice here that the expected value of mu tilde is equal to mu. Okay, so this result here shows that for SRS, mu tilde is unbiased for mu. And we can prove that fairly easily. So we're going to take the expected value of mu tilde. This is going to be the expected value of 1 over little n multiplied by the sum of I in u of capital I choose little I multiplied by y subscript I. Okay, so the expected value operator is a linear operator. It multiplies the random variable in each expression by the constants that are associated with the expression. In this situation, we have two constants. We have little n, which is the sample size, and we also consider yi to be a constant as it's an observed value from the sample. Now, this part of it is a little bit unfamiliar because usually we would consider the yi to be the random variable. In this case, we're considering the I subscript I, the indicator variable, to be random. So we then have, under this formulation, 1 over little n times the expected value of the sum of I across u. Oh, sorry. Okay, yeah, we'll write it like this. We have to write it like this. I times yi. Okay. All right. Okay, now we need to work out the expected value of I little I. It's a fairly easy calculation, but the first thing that we need to recognize when we do this, actually, let me also just to try and break it down into the steps. Okay, so this is required. And then we'll just write here, what is the expected value of I little I? So that's our little aside, just to finish off the proof. Okay, so we want to work out the expected value of I subscript little I. We determined on the previous slide that the inclusion probability for each individual observation is little n over capital N. Okay, so we know that the probability I is in S is equal to little n over capital N. Okay, so therefore, the probability that capital I subscript little I is equal to 1 is also little n over capital N. So this is actually the same probability. So the probability that an observation is selected for the sample is the same thing as an observation having an indicator of, has the same meaning as when an observation has an indicator equal to 1. Okay, so the probability that that observation I is in the sample is the same thing as the probability that observation I has an indicator equal to 1. So therefore, the probability of observing observation I, regardless of how you write the probability expression, is little n over capital N. All right, the next part of it, capital I choose little I, so the indicator variable, this is well, it should be a very familiar type of random variable. Does anyone know what kind of random variable this indicator is? It would actually be the same kind of random variable any binary indicator would be. So the question is, what random variable or what random variable distribution does the indicator capital I choose little I follow? It starts with a B. Yeah, Bernoulli, nice. Okay, so the indicator variable is a Bernoulli. And then as a reminder, a Bernoulli random variable is, well, it would probably be considered the simplest possible discrete random variable. It's a random variable that can take on two values, and the probability of taking on each value is complementary. So the expected value, so if capital X is Bernoulli, with probability of success little p, then we can write that the expected value of capital X is equal to the sum across X times the probability of X, which is actually just the formula for the discrete random variable. But I didn't define the values that X takes on, so it makes more sense to write it in this way. So therefore, the expected value of capital I choose little I is equal to 1 multiplied by little n over capital N plus 0 multiplied by 1 over little n divided by capital N, which is little n minus n. All right, so then we can say that this thing here is just the sum from from I across I and U of little n choose capital N multiplied by yi. And then you can see that what ends up happening next is you end up with 1 over capital N multiplied by the sum of I and U of yi. Right? So now we have the sum across all observations in the frame divided by the frame size, and that is the definition of the population mean, hence the result being unbiased. Right. So that's the proof for the estimator for the mean. So we can see from this proof, I mean, we already established it at the start, but this is how we can show using the random variable notation, so introducing the indicator, that the expected value of mu tilde is equal to mu. Now, technically, for mu tilde, you could, if you assume that yi is random, you can pretty easily arrive at the same conclusion that we have shown here. However, when working with the variance expression, it's much more, the proof is more difficult, in my opinion, without using the indicator variable, hence why we introduced it. Okay, so the second thing that we need to do is start the journey of proving that the variance of mu tilde is equal to 1 minus little n over capital N times sigma squared over n. Now, a few notes about this estimator, and we'll come back to these notes in a little bit once we work through the proof, but you'll notice that the expression for the variance of mu tilde should be a bit familiar. In particular, you'll notice that we have sigma squared over little n, which is traditionally the quantity that we associate with the variance of our estimator. So as we have studied, in particular, the central limit theorem, but even more generally, just the properties of the sampling distribution of the sample mean, we have consistently showed that the expected value of our estimate of mu is equal to mu, and the variance of our estimate of mu is equal to sigma squared over n. So we have that quantity here in our derivation, but then we also have 1 minus little n over capital N. This 1 minus little n over capital N is a constant that corrects for finite population size. So in a little bit, we'll come back to talk about this constant and how we would apply it in our applications. But in general, the reason that this term exists is because we are assuming finite population size. So we are accounting for the fact that our sample size might be a fairly large portion of this, of the sample frame size. Sorry, not the population size. That's tough to get used to. All right, so the variance of mu tilde. So this is a pretty involved formula. Like we did with the expected value of mu tilde, we'll have to make little sort of side arguments along the way to prove out different aspects of the formula. But the goal is essentially just to show that the variance of mu tilde is equal to 1 over little n divided by capital N multiplied by sigma squared over little n. So this is what we're going to work toward showing. But along the way, we'll have to make little, we'll have to pause to make certain arguments to help prove that theorem out. All right, so before we start, we need to recall the definition of the variance of a constant multiplied by a random variable. All right. So I'll just write here, required definitions. 1. Okay, so this is a result that you would have seen in Stat 265. I'm pretty sure I taught this in Stat 265, but is typically something that kind of gets pushed to the side because it doesn't come up a lot, but we will need it in our following derivation. All right, so if we have the sum across a sample, so this is just the general definition, and then we're going to apply it in the context of our notation in a little bit. So we have AI multiplied by YI, all right? So in this situation, the AI is constant and the capital YI is random, okay? So the variance operator is closed under addition and subtraction, and any constant that multiplies by a random variable within the operator is squared. So the first simplification we can make here is that this thing is going to be the sum from I equals 1 to little n of AI squared multiplied by the variance of YI. Okay, now if the YI are independently distributed, this expression is now finished. However, we have seen that in the context of selecting a simple random sample, each time we choose an observation from the sampling frame, the number of observations that we have left to choose from and the number of observations that we have left to select changes. So it is not reasonable to assume that each observation in the frame is independent. More in particular, yeah, let's say it like that. So it's not reasonable to assume that each observation in the frame is independent because one observation being chosen changes the probability of the next observation being chosen. All right, so because that is the case, we then have to account for the relationship between the random variables. So then we would add on a summation for all I not equal to j, ai aj multiplied by the covariance of yi yj. Okay, so this is the complete definition of the variance of a constant multiplied by a random variable when the random variable cannot be considered independently distributed. The second definition that we require then is that of covariance. So the covariance between two random variables is equal to the expected value of their product minus the product of their individual expected values. All right, so let's take the first definition, so the first required definition, and let's apply this in the context of our SRS scheme using the indicator variables that we have established beforehand. So we're going to write here the variance. Okay, so let's just try and break this. I want to try and break it up so it's a little bit organized. So we'll call this step 1. So we're going to have the variance of mu tilde is equal to the variance of 1 over little n multiplied by the sum for I and u of I, capital I choose little I times yi. All right, so as a reminder, the capital I choose little I is the random variable and everything else is constant. So the next part here, we will have the sum for I and u okay, sure, let's just do it like this. So we'll have 1 over little n squared times the variance. There's my summation. Can I pull this? Yeah, okay. Multiplied by yi squared times the variance of I choose I. All right, just make sure. Okay. Oh. Oh, sorry, it froze. Okay, one sec.
What's happened?
It just froze. One sec.
So are we planning to touch the confidence interval on Wednesday?
Sorry.
Are we planning to are we planning to cover the confidence interval on Wednesday?
Yeah, we should be able to get to it on Wednesday. Sorry, guys, one sec. I'm just waiting for the. Okay, so here we go. Now the second part here, we need to work out the form for our covariance. So we will have. Oh, come on. Oh, sorry. Ugh. All right, there we go. We're back. Okay, and then we're gonna have the sum for all I not equal to j, 1 over n squared multiplied by yi yj times the covariance expression like this. Okay. All right, so we can then simplify this by pulling the 1 over n squared out front. So this will give us 1 over n squared multiplied by the sum I and u yi squared times the variance of I plus the sum I and j yi yj covariance I j. All right. Okay, now we have an expression for the variance of mu tilde. So we have to get two things out of this expression. We need the variance here, and we need the covariance here. Right? So obviously, because we're basically out of time now, the variance for capital I choose little I, we can derive fairly easily because we know that capital I choose little I is Bernoulli. So we know the properties of the variance operator for a Bernoulli distribution. The covariance will take a little bit more time to establish, but we can work through the properties of this fairly easily as well, since capital I choose little I and capital I choose little j are both discrete random or both binary random variables. Okay. So what we'll do on Wednesday is we'll compute both of these attached parts, so the variance and the covariance, and then we'll plug them in and we will establish the rest of the proof. All right, sorry for the technical difficulties. I'm not really sure if that's an internet issue or a battery issue or whatever, but hopefully they're minimal throughout the semester. And as I mentioned, so on Wednesday, we'll keep working through this proof and we'll just see where we are by end of class Wednesday regarding the first assignment due date. All right, so have a good day, everyone. And if you have any questions, please let me know.